Welcome back. Today we're celebrating our 20th episode of Q&A Monday. For today's episode, I want to address assembly processes when tightening threaded fasteners, screws, nuts, bolts, and barrels. I've received several questions about tightening fasteners, the latest of which was how I tighten my action screws and whether I've experimented with their torque. You probably noticed that I'm referring to fasteners. That is purposeful in this video. The YouTube rules do not allow me to show or describe processes for the assembly, building, etc. of our favorite high-speed freedom projectors and hole punches. So I will be talking about the general concepts behind finding and applying the correct torque for your threaded connections. This video is going to bounce back and forth between technical engineering stuff and general advice, so bear with me. Do stick around to the end, or I'm going to save you an immense amount of grief when you torque your fasteners. Let's start on the experimentation part. I have both the Kelbley's Golden Bear action, a flat bottom design, and the perfectly round Bernard action. Let's consider bedding for a moment. I found that with a completely stress-free bedding job, action screw torque doesn't seem to have any major effect on either of my actions. Bernard recommends a V-block for mounting their actions, and I have a couple of stocks with V-blocks installed. I believe that torque can have a far greater effect in a V-block than in perfect glass bedding, but I don't have any testing behind that belief, and the Bernard action is so stiff that it would likely take some pretty crazy torque differentials to see a result on target. I'll have to do a separate video on that subject. For today's video, I'm going to focus on the bedded stock designs that I have. I'm not going to make a torque recommendation for you and your stock because my stock to action interface most likely differs a bit from yours. To be transparent, I torque my action screws with a bedded action to 50 inch-pounds. But that isn't the whole story, and I can't let you get away without explaining it a little bit. Let's take a look at the basics for a moment. In essence, torquing creates a force between the mating surfaces. In the case of this bolt, I'm placing a force between the head of the bolt and the block it is screwed into, squeezing them together. The amount of force created is a function of several factors: thread diameter, torque applied, and friction, to name three. For someone assembling a threaded connection, only two of those are under their control: torque applied and, to a limited extent, friction. Torque seems self-explanatory, but friction can be a bit confusing. Friction can be reduced most times with lubrication. Lubrication may not always be a good thing in a threaded joint. Now, that lubrication can come from dry lubricants, grease, oil, or this one will shock you, thread locking compound. That's right, your favorite thread locker changes the amount of force you're placing in a joint. When wet, thread locking compounds tend to act as a lubricant in a joint. That lubrication will increase the force applied in that joint for any given amount of torque. In a lot of cases, the use of a recommended torque for a dry, unlubricated fastener will cause permanent fastener deformation or even failure if the same torque is applied with a lubricated fastener. Now guys, if this video is bringing you value, would you do me a favor and like and subscribe? I appreciate your support as we grow. All right, back to our discussion. Thread lubrication isn't the only lubrication to consider. Lubrication in the joint itself, under a bolt head for example, changes the force as well. I'll leave a link to an online calculator in the description. My advice here is simple. Understand the recommended torque value and lubrication or lack thereof for that recommendation before you apply torque. In case you find yourself having to retorque something that had thread locker on it, you must completely disassemble the joint and clean out all of the old thread locker in order to properly torque it again. It goes without saying that dried thread locker significantly changes the required torque values. Now, please don't get too wound up in the details here. The general principles are what we're talking about and remain the same even as we drill down pretty deep. For our quarter 28 action screws, I'll save you the math and throw some results out. For a dry, unlubricated thread with an assumed friction, the 50 inch-pounds generates a per fastener force of around 1,100 pounds. If we lubricate that same fastener with some white grease, the forces go up to about 2,200 pounds, double the initial value. These are all based on a lot of generalizations and assumptions, so some caution is necessary. The forces squeezing the parts together also create an equivalent tension force trying to tear the bolt or screw apart. The screws and threads are only so strong, and we have to understand how strong they are in order to know if we're hurting anything. For our screws, we need to know the yield strength of our chosen fasteners. That can be pretty difficult to ascertain at times. For my action screws, I know that the base metal has a yield strength of approximately 90,000 psi. If I take the cross-sectional area of the screw thread minor diameter and multiply it by 90,000, I find that my fasteners are capable of handling approximately 3,100 pounds without yielding. As a generalization, I found that torquing to 70% of that yield number is a reliable way to torque a connection. In my case, 2,200 pounds is closer to that target force, and torquing a lubricated joint seems to me to be more precise, so I torque my bolts lubricated to 50 inch-pounds on my stocks. Now, if you're using hardware store screws, your yield strength will be different. Please use caution. Does that mean that I have it all figured out? No, not quite. If we are engineering a joint and have a bunch of assumptions like we do in this case, we have to test those assumptions. For our 1/4-28 screws, we would take 1, measure the overall length of the screw to the best of our abilities, then torque it, loosen it, torque it again, loosen it again, and torque it again before removing the screw and checking the overall length. If the screw length got longer, we've gone beyond yield and need to recalculate with a different set of parameters. That isn't to imply that joints are never designed to stress the fasteners beyond yield, the point of permanent change in shape, that is. I just don't think that it's appropriate or necessary for action screws. Let's take a few minutes to understand how to accurately apply our torque values. My day job is in aviation. I've been doing this for over 30 years, and during that time, I've spent more than a little time hanging off the end of a torque wrench. I can tell you from experience that very few people, without training, can pick up a torque wrench and use it properly to apply the desired amount of torque. There are many tools out there designed to apply torque. Click-type torque wrenches, breakaway torque limiters, electronic torque wrenches, and finally, one of my favorite tools of all time, the bending bar torque wrench. Yes, I use one of these. Since the click-type torque wrenches are the most common, let's use that as the basis for this discussion. The principles apply to all the types, but the click type is the easiest to demonstrate with. These are very simple devices. Once set for the desired torque, the user applies force until the handle breaks or clicks over, indicating the desired torque has been achieved. Seems easy, right? With correct technique and appropriate wrench sizing, it really is that simple. Let's go over proper technique for a moment. In order to get the desired set torque when using the wrench, the force needs to be physically applied at the center of the hand grip and nowhere else. Not only that, but the force has to be increased slowly in a smooth fashion while the fastener is turning. You can't torque a fastener that is stationary and expect a good result. It just won't happen. There's a hint in here for checking the torque of your fasteners. That is to loosen them slightly before retorquing. Likewise, pulsing the force by bouncing on the torque wrench because you aren't physically strong enough to pull or push it isn't going to provide the set torque. Please don't do that. If you aren't strong enough, either get a bigger torque wrench or use a torque multiplication method. Bouncing on a torque wrench is equivalent to applying spot torque. You know, applying force until you see spots. When the torque wrench does click, you must stop applying force immediately, ideally before the breakaway mechanism bottoms out. When done right, it looks like this. Which brings me to setting up the tooling. A torque wrench is designed to be used with a socket. That way the rotational axis of the wrench head and the fastener being torqued are aligned. If we induce any misalignment, like this, we have to start calculating the actual torque applied relative to the torque wrench indication or setting. For those of you unfamiliar with that concept, and for the sake of time, I'll put a link in the description on how to do that calculation. Last but not least, sizing the torque wrench for the job is as important as technique. As an ugly generalization, torque wrenches are not reliable below 20% of their maximum setting. For example, my 200 inch-pound torque wrench is only good for about 40 to 200 inch-pounds, regardless of the markings. A 250 foot-pound torque wrench should not be used for any torque less than 50 foot-pounds. That means that you will need a special torque wrench for the low torque screws like scope ring caps and rail screws. Don't assume that the torque wrench can apply 20 inch-pounds just because there's a setting for it. In conclusion, you need to understand your recommended torque, the conditions for that recommendation, and use a torque wrench to apply torque correctly with good technique and a firm understanding of the limitations of your tools. All right, guys, that's all I have for today. Shoot straight, torque your fasteners accurately, and I'll see you in the next video.